Hi there. Welcome to Weapons of Math Instruction and Happy Pi Day. In celebration of this day, I'll be releasing a short video about pi every day this week. Sort of like a little bite of pie each day. Today's video is a get-to-know-you video on everyone's favorite irrational number, pi. This video will be in 3 short segments, starting with the fundamental question, just what is pi? And here's one way to answer that question. Pi is the number of diameters of a circle that will wrap around the circumference of the circle exactly once. Now I'm going to get a little mathy on you and introduce some symbols. If we call the circumference of a circle c and the diameter d, then we have the ratio c over d equals pi. That's how I express the first bullet point in symbols. The circumference is of course the distance around the circle, while the diameter is the distance across the circle. To illustrate all this, we're going to take the circle apart and reassemble it. So here is a section of our circle, and the length of that section is exactly equal to the diameter, d. And here at the bottom of the screen, I've straightened that section out. Here's another section of our circle of length d, and here it is straightened out. And another. And as you can see, we're not quite home yet. We've got this little gap here. Now, there's not enough room to fit a 4th full diameter in that gap, but rather a little piece that's approximately 0.14159 times the diameter. And here at the bottom of the screen, I've got these 4 pieces laid out end to end. And the combined lengths of these line segments is exactly the same as the circumference of the circle. And I express that with this equation here. The circumference of the circle equals d plus d plus d plus approximately 0.14159 times d. And if I combine these 4 like terms, I find that the circumference of the circle equals d times 3.14159 ... And this number here next to the d is pi by definition. The ... at the end here indicates that the decimal expansion of pi never terminates. It also never repeats. I'll explain these facts in detail on day 5 of this week in a video called Pi is Irrational. Now if we rearrange our ratio that defines pi, we get a handy formula for the circumference of a circle, which is c equals pi times d. A more familiar version of this formula is written in terms of the radius r, which is 1/2 the diameter, and it goes c equals 2 pi r. In the next segment, I'll talk about angles in radian measure and how pi fits into it. Most people who have studied angles are familiar with angles in degree measure. Now an angle can be formed by 2 rays or by 2 line segments that have one endpoint in common. Here I have a figure in which 2 line segments are coincident, and so they form an angle of 0 degrees. If I rotate one of the line segments 30 degrees counterclockwise about the origin of the coordinate system, I get this angle. Rotating 15 degrees further, I get this 45-degree angle. Rotating the line segment to the vertical axis gives me this 90-degree angle, also known as a right angle. For reasons we won't get into today, right angles are special, which is why this block symbol is used to denote them. And if we keep rotating the line segment until we get back to where it started, then we will have swept out an angle of 360 degrees. We will also have swept out a complete circle, which means that there are 360 degrees in a circle. Now, dividing a circle up into 360 1-degree slices isn't the most natural thing to do geometrically. Why 360? Why not an even 400? Or why not go all metric with it and divide the circle into 100 pieces? It turns out that there's a geometrically natural unit of angle measure, and that pi fits naturally into it. And that unit of angle measure is radian measure. In this system of measurement, there are 2 pi radians in a circle. To give you a sense of how big a radian is, I've drawn an angle that is exactly 1 radian. It's approximately 57.3 degrees. We can convert angles from degrees to radians by using the conversion factor implied by the first bullet point, which tells us that there are 2 pi radians per 360 degrees. For example, the 30-degree angle from the previous slide can be converted to radians by multiplying the 30 degrees by 2 pi radians over 360 degrees. and it works out to pi over 6 radians. Radians are such a natural unit for angle measure that they are the default unit, and we don't need to write the unit rad after angles when they're written in radians. It's just assumed. And so here, I'll convert the 45-degree angle from the previous slide to radians while omitting the rad, and it works out to pi over 4. And finally, 90 degrees converts to pi over 2 radians. In most books on pre-calculus or calculus, special angles are displayed on what's called the unit circle, which is a circle of radius 1. And here is that unit circle with several special angular positions labeled in degrees and in radians. And also, corresponding points on the circle are labeled with their xy coordinates. I omitted the line segments going from the origin to each of these points because, as you can imagine, this drawing would be a lot more cluttered if I put them in. This last segment on arcs and sectors is where I hope to convince you that radians are indeed the most natural unit for angles. First, an arc is a section of a circle. And a sector is a geometric figure formed by an arc and 2 radial lines. So here I've drawn a sector, and the 2 radial lines are labeled R, and the curvy part, that's the arc, that's labeled S, and the angle that's intercepted by the arc is labeled with the Greek letter theta. The arc length, S, is found using a neat little formula, S equals R theta. But there's one catch. In order for this formula to be valid, theta must be in radians. It is possible to develop a formula for arc length where theta is in degrees, and here it is, but this is ugly, and we're going to forget about it and never speak of it again. Now here's an interesting question. What if theta equals 2 pi, so that our arc is an entire circle? We'll start with our formula for arc length, S equals R theta, and then we'll plug in theta equals 2 pi, and we get that the arc length S is equal to 2 pi r, which is exactly equal to the circumference c of the circle as we discussed in the first segment of this video. And this is exactly as it should be. I want to stress that S equals R theta only reproduces the circumference formula if theta is in radians. And with that, my dear viewers, we have come, wait for it, full circle. Thanks for watching, and tune in tomorrow for another bite of pie. Hey everybody, if you enjoyed this video and want to see more like it, then please do follow me on my socials. You know you want to.